This lesson is about complex numbers, polar and rectangular form. Here's a complex number. As we know, a complex number is a real plus an imaginary term. We saw in a previous video that complex numbers can be plotted or thought of as ordered pairs directly above their real part and imaginary term, as shown. And when you have a complex number or a point, and you're essentially given its x and y coordinates, as we have in these two cases, we refer to that format or that expression as a rectangular or a Cartesian way to represent the point or the complex number. We discovered in a previous video that there's other ways to describe the location of a point. This point, for example, in addition to being the point 2, 3, happens to be radical 13 away from the origin, which is about 3.6-ish. And it's also located at approximately a 56-degree angle. And so, in mathematics, we often refer to that point by, rather than stating its x and y coordinate, stating its modulus or distance from the origin and its argument or its angle. When a point or complex number is referred to by its distance and angle rather than its x and y coordinates, we say that it's expressed in polar or trigonometric form. There's one additional way to express this point using the same numbers in a very unusual format. This is called the cosine I sine format, and as strange as it looks now, if you're seeing it for the first time, you get used to it after a while. We'll see many more examples that will clarify what that means. So let me summarize the idea between polar and rectangular expressions of complex numbers. If we have a point or a complex number and we want to express it in rectangular or Cartesian coordinates, we need to know its x coordinate and its y coordinate. And if we do, we can express it as an ordered pair or as a complex number. On the other hand, if we want to express that same point in polar or trigonometric form, we can do that provided we know its distance from the origin and its angle, and we can similarly express the point that way, or using the unusual cosine I sine format. One skill that's important is being able to convert between rectangular and polar. So let's look at an example where we have a complex number in rectangular form. And if we're going to convert that to polar, we need to find it on a graph. Let's recall that rectangular form is one in which we're given the x coordinate and the y coordinate, which I will put there where these tick marks are. And therefore, the point corresponding to this complex number is right here above and across from the tick marks. So if we want to convert this to polar form, which is what we're being asked to do, we're going to need to know its distance, r, and its angle, theta. Now, to go about finding theta, I think it might be easier to make a triangle here and find the angle beta instead. If I can work within this purple triangle to get r and beta, then I'll know theta, and I'll know everything I need to know about the polar form of this complex number. Now, since we know the x and y coordinates, we know these lengths here. And knowing those lengths there make it a little easier to find beta and ultimately theta as well as r. One thing you may notice about this purple triangle is that it's not just any triangle. The ratio of legs is radical 3 to 1. And that's a unique characteristic of a 30, 60, 90 triangle. And therefore, since we have a 30, 60, 90 triangle, we know that beta has to either be 30 or 60. But let's recall that the 30-degree angle is always opposite of the shortest side, which in this case would be 4, which means this angle at the top is 30, and therefore beta must be 60. And the reason I wanted to find beta was so I could ultimately find theta, 180 minus 60, and that gives me theta. Now as far as r, finding r for the polar form, you may recall that the hypotenuse to short leg ratio in a 30, 60, 90 triangle is always 2 to 1. In other words, the hypotenuse is twice as long as the short leg. Since the short leg is 4, the hypotenuse must be 8. 4 times 2. And now that we know the modulus and the angle of this complex number, we can express it either as an ordered pair or using cosine I-sine notation. These are both totally acceptable ways to express this complex number. You may also express them in radians. If you're not comfortable converting to radians, leave them in degrees. No one will fault you for that. But it's important to know that you will see these expressed in radians from time to time. So you have to know how to convert. Let's look at another problem where we're given a rectangular form of a complex number, and we're asked to convert it to polar. So how do we convert 5i into polar notation? Well, the only way to convert between rectangular and polar is to know where the complex number is in the plane. One way to easily find 5i is to think of it as 0 plus 5i, just using a rule from kindergarten that 0 plus anything is itself. But thinking of it this way helps, because it reminds us what our x and y coordinates are of this point. So this point is effectively the point 0, 5. So to convert it to polar, we need its distance r and its angle theta, but without any algebra or calculation whatsoever, it's obvious that r is 5 and theta is 90, and therefore we could express it as 5, 90 degrees, or in radians if you prefer 5, pi over 2, or in cosine I-sine notation, effectively the same thing. Let's turn our attention to converting the other way, this time being given a polar complex number. So here's a complex number in polar form, and we're being asked to convert it into rectangular. Again, the only way to convert is to have a good picture of where this point is, so let's analyze that. 5 pi over 4 turns out to be 225 degrees. You can always look up how to convert radians to degrees if you need to. It's a simple multiplication conversion factor. But that means that my complex number must be at a 225 degree angle. And furthermore, it's got to be 6 spaces from the origin. So my point would have to be right there. But again, to convert to rectangular form, which is what we're being asked to do, I need to know the x and y coordinates of that point, because that's essentially what rectangular form is. So I've got to find x and y. Well, one way to find x and y is to realize that you have here in this purple triangle that you have a 45, 45, 90 right triangle. First of all, this angle is 45 because it's 225 minus 180. And if that angle is 45, so is the other acute angle. And therefore we have a 45, 45, 90 triangle. Well, you may recall that the hypotenuse to leg ratio on a 45, 45, 90 triangle is radical 2 to 1. That means since my hypotenuse is 6 and my legs are shorter than that, I'm going to have to divide by radical 2 to get the legs. Now I didn't show the algebra here, but some basic rationalizing the denominator and simplification shows that this works out to 3 radical 2. And I've just found the length of the leg. And since both legs are the same, I've effectively found x and y. So back to converting to rectangular coordinates. If the lengths of x and y are both 3 radical 2, this must be the rectangular expression for this complex number. Notice both the x and y here are negative because we're in quadrant 3, and that's the nature of quadrant 3. By the way, this thing here is an acceptable answer, but you may often see it written this way with the I in between the 3 and the radical 2, and there's nothing about that that's mandatory. It's just a simpler looking way to write the same thing. Let's look at a problem now that's also converting polar to rectangular, but will end up requiring a calculator, unlike the previous problem. So if we want to convert, we need to have a graph and have a good image of where it is. 310 degrees wraps around to quadrant 4, and this is my distance from the origin, so my point has to be out here 2 spaces away. And again, if I want to find the rectangular coordinates here, I essentially need to know the x and y coordinates. So this once again becomes a problem about finding triangle lengths. But here's what makes this problem different from the ones we've seen so far in this video. This is a 50-degree angle, 360 minus 310. And if that's a 50-degree angle, then I don't have a special triangle. I don't have a 30-60-90 or a 45-45-90 or anything that I have special talents in working out without a calculator. So this would be the kind of problem where you would have to resort to using one. No problem. Using basic trigonometry, we can find out what x and y are. I set up a sine equation to find y and a cosine equation to find x. And doing some very basic algebra will lead me to approximations for y and x. And once I know my approximations for y and x, I can express it in rectangular form. Notice the y coordinate is negative here because we're in quadrant 4. Here's one more problem that requires the use of a calculator, as we'll see. So if we're converting to polar form, and I believe the directions at the top are wrong, we would be converting from rectangular to polar. There we go. If we're converting from rectangular to polar here, I need to look at the graph. Well, I've got my x and y coordinates. That tells me my complex number is here in quadrant 2. To convert that to polar, once again, we need its distance from the origin, or modulus, and its angle. One smart way to find theta would be to find beta first. So I set up a trigonometry equation to find beta, did some basic trigonometry. This is a valid conversion from tangent to inverse tangent because beta is an acute angle, and a calculator will tell me that beta is approximately 53 degrees. 180 minus that will give me theta, and I now have the argument of this complex number. I also need the modulus r. To do that, I could use the Pythagorean theorem to find r. I didn't show the algebra here, but some basic arithmetic will show that r is 5. And now that I know the distance and the angle of this complex number, I can express it in polar form or cosine I sine form, which is another version of that. And that concludes the lesson.